I think we're ready to move on to our next speaker, who is Julian Schmidt, coming from GFDL at Princeton, who is going to continue on the theme of snow drought.
Cool. All right. Let me just put this in presenter mode. Does that look good? Cool. All right. My topic today is called Illuminating Snow Droughts, the Future of Snowpack in the Western United States. So we just heard from Ben, who was talking about some of the history. And so I think this is actually a really well-placed pairing of talks. So I'm going to be talking more about the future. So to jump right in, some motivation. Ben actually kind of covered this already, so I don't really need to talk too much on this slide. Basically, we're defining snow drought as anomalously low snowpack. So this GIF here is showing the maximum SWE across the Western United States in 5-year intervals. Similarly, I find it helpful to talk about, would be remiss to talk about snow drought without talking about temperature and precipitation as well. So in this case, I plotted a bunch of snow droughts in the temperature and precipitation space, and I like to think of these kind of I like to think of these as both warm and dry classifications. So here, I've kind of labeled these as like ice cream cones, right? And we see that most droughts here are tending to double dip in that warm and dry regime. So what's at stake more broadly? Water shortages, agriculture, and wildfires are all conditions that are exacerbated by more frequent snow droughts. So for me, when I was conducting research for this project, I was out in Bozeman, Montana. And this is a picture of some of the smoke that was out there. So it really, these snow droughts affect large regions across the Western United States. And probably a lot of you guys have experienced some of this recently. So let's introduce some of the data sets that we were working with, as well as some historical patterns. So we just heard from Ben Livna. I actually used one of his data sets in my project. So I used one of his blended model and observational data sets that ran from 1915 to 2011 with daily SWE temperature and precipitation, and that's continental US. We also used Tom Delworth's GFDL Spear. That's kind of a long title there. It's using up-to-date land, ocean, atmosphere, and ice models using an experiment that runs both the historical period, similar to the Livna data set, as well as two modeled future scenarios under different forcing. So SSP5 8.5 and SSP2 4.5. So let's go into how exactly we classify snow droughts. So we take raw snowpack data, and we then aggregate it to a particular region or across a half-degree grid, so just looking individually at grid cells. We can then look at the distribution of the regional climatology. So here we're looking at a ECDF, or empirical cumulative distribution function, for the max SWE for the upper Colorado region. And basically this gives us a sense of what do most years look like and what do the extreme years look like. What we can take from there is we can simply apply an inverse normal CDF and then classify them similar to the US drought monitor, how they do it, to get basically classification for a given region or a given grid cell at a particular time. So this is either a month or a year. So for example, in this graphic here, we see that the Pacific Northwest region is experiencing some kind of moderate to severe drought. Specifically, let's look at kind of now the historical changes across the regime here. So first, to validate the Spear large ensemble, what we want to do is we want to compare how that does against the Livna data set. And so as we're concerned primarily with changes that are going to happen in the future, it's really important to compare changes to changes, right? So we're not looking at the absolute values of these conditions here, we're looking at the changes. And so what we do is we simply count the number of droughts that occur in each of the early and late historical, and then we can simply calculate a percent increase. And so what the key takeaways here is that we're able to plot this histogram We see that the LIVNA data set is experiencing a fractional increase in snow drought conditions, while the SPEAR is predicting a more significant increase if we're looking at the ensemble mean. However, importantly here, the LIVNA estimate is within the SPEAR ensemble spread, and so that lends confidence to our analysis and to the SPEAR ensemble more generally. So we can look at that trend across a variety of parameters. We can look at snow droughts, we can look at meteorological droughts, or we can look at temperature changes. We found that the SPEAR and LIVNA agreed most often on the snow drought and meteorological drought, while the temperature was a little bit, they agreed slightly less. And we think that might be due to differences in gridding or SPEAR having trouble resolving temperature extremes. That's less important for our snow drought classification. So let's jump into looking at trends into the 21st century. So the first graphic here is 6 panels, one for, I sampled 6 decades across the temporal space that we had. And I basically restrict the data space to historically snowy regions. And then we're coloring each grid cell here based on the percentage of months in that decade which experience severe snow drought. And what we can see is that historically, these percentages are around 8 or 10%, and then conditions rapidly worsen after about 2000. So this is for the SPEAR ensemble mean. The whole purpose of having a large ensemble is that we can get a measure of the variability of these conditions, right? And so here we're plotting each of these trends for each of the 30 ensemble members. Again, we have that average that we saw on the last slide here in the darker line. And then we've plotted the future as well. And so what we can see is that historically, again, roughly somewhere between 5 and 10% of months experienced this snow drought condition before 1990 and then we have this sharp uptick with this almost hockey stick effect moving in towards the end of the century. And so this is really concerning under a high emission scenario. Going back to our ice cream cones and our kind of climatology behind these, is temperature and precipitation. What's really helpful to look at is how these regimes are shifting over time. So again, we have those classifications. A simple thing we can do is take the average of these months, right? So looking at how those averages shift in time should be a good indication of what is driving these future changes in snow drought that we've previously observed. And so we can do just that. And what we find is that historically, we can see these drought months are both primarily dry and primarily warm. But as we move throughout the 21st century, we find that transitions to both increasingly warm and increasingly wet conditions. And so it seems like towards the end of the 21st century, that the precipitation might really not matter at all. It might be that these conditions are so warm that we're having trouble even even staying below those conditions. And so that convergence there suggests that snow droughts are really going to be dominant feature by the end of the century. Okay, so you may say, okay, Julian, that's all well and good. Maybe lots of the regions are going to have less snow than they had previously, but what exactly are these impacts going to look like? So to address that question, we focused on the total SWE comparing the April 1st SWE across the Western United States. So here what we're doing is we're looking at a slightly different classification. Those are given with our kind of snow stake here. So we're going to primarily be interested in no snow conditions because those are the most extreme and likely to have the most impacts. So what we can do is then we can take those classifications, we can aggregate them as an area fraction for each region, and then we can plot that through time. So that's what this graph on the left is doing. It's simply plotting those conditions through time And then that red line is taken a rolling average, so you can kind of see what the dominant regime is across those conditions. What we can then do is set a area fraction threshold to see, okay, when is there a transition happening between kind of this more historical and into this no snow regime, right? So if we set this threshold pretty high, we're going to get very extreme conditions. And that's what the panel on the right is doing. We're looking at the transition times for each of the 5 Western watershed regions to see when those transition to this really extreme 90% of the area is experiencing these no snow conditions. Interestingly, California and Lower Colorado seem to be experiencing those conditions first. And that's maybe indicative of their latitude, whereas the other conditions seem to occur more towards the end of the 21st century. So let's take a quick dive through a comparison of that higher emission scenario that we've looked at with kind of a lower emission scenario, and see what that can do to lessen those conditions. So first of all, we notice that the drought occurrence is significantly reduced under the lower emission scenario. Just give you a minute to look at these figures here. And then we can look at that, again, that aggregated figure. We see that divergence from that higher emission scenario where it kind of tapers off towards the end of the century. It's kind of consistent with how they're modeling changes in carbon concentrations. We do see also here a slight increase in the variability of the lower emission ensemble spread as well. Finally, for the climate shifts, we do see again that it's just less acceleration moving forward, and that sort of it seems to stall towards the end of the 21st century for these drought months at least. We also see this interesting turn here where the temperature doesn't increase for a couple of decades really dramatically, whereas the precipitation for these drought months does. And finally, for the transition to no snow conditions, what we found that the lower emission scenario didn't actually reach that threshold didn't reach that 90% threshold by the end of the century. So we looked at a lower threshold. What we found is that lots of these transitions occur a lot later. So there's, on average, there's a less severe outlook. But there's also a non-trivial subset of these lower emission scenarios here that do go snow-free during a similar time as the higher emission scenarios. So that's something really to be of note, that we really only get one realization of the climate, right? And so where's that going to fall? Is that going to fall towards the end of the century or earlier? So that's a question that's important to ask. And then my conclusion slide, yeah, perfect. We found that snow droughts have already increased significantly to date. They're expected to really accelerate in the coming decades. They're driven primarily by increasing temperatures and not hydrological droughts. And finally, a lower emission path will delay a no snow transition, will likely delay a no snow transition, but the ensemble variability indicates that this timing is increasingly uncertain. So again, I'd like to thank Noah Hollings, as well as my mentors. I'd like to thank the host for this session, and my contact is listed below. Thank you.
Awesome, thank you, Julian. That was great. In the interest of time, we're going to have to move on right now, but there are 2 questions in the chat that we'd like you, certainly one from Ben and one from Mike Hobbins. If you can answer those, and then maybe we can bring back and talk about it at the end. So thanks.
Perfect. Thank you
so much.
Yeah, thank you, Julian.